Good evening to all. My name is Eleftherios Petavratzis, and I am PhD candidate at the Laboratory of Nonlinear Systems, Equation and Complexity at the Department of Physics of Aristotle University of Thessaloniki. Today, I would like to discuss about a topic that it is very common among researchers. It is based on the creation of fast and efficient methods for controlling the behavior of mobile robots in order to cover a given area. In our case, we decided to create random-like motions, and for that reason, we decided to use a chaotic system for controlling the autonomous mobile robots. In this presentation, first we will talk about autonomous mobile robots, and we will present some examples of them. Then we will create a chaotic path planning method for controlling the behavior of our mobile robot. Then we will create the memory technique and we'll compare it with the chaotic path planning method that we have created before. And finally, from this comparison, we'll have some conclusions and the future work that it could be done. I think that all of you know what is an autonomous mobile robot, but I would like to say that they are robotic systems that are performing tasks without the presence of a user. Their use is very crucial for space missions, in fires and other military missions, such as scanning an area for explosives or dangerous materials. Here you can see some very common applications of autonomous mobile robots, and you may recognize the vacuum cleaning robots, the robots for space missions, and the firefighting robots. In our work, we first want to create a random-like motion sequence using a chaotic system and a model operator. And secondly, we want to create a strategy for a complete and fast scanning of a given area with the use of the memory element. So what is a chaotic system? The definition is very simple because it is a dynamical system that it is governed by deterministic laws and it is very sensitive to its initial conditions. That means that even a slight change in the initial conditions or parameters could force it to have a completely different behavior. Here you can see two examples of chaotic motion, and you can recognize at your right that we have three double pendulums. They are starting from the same position, and after a while, they presented a completely different behavior. We have two very simple tools for studying the behavior of chaotic systems, and they are the bifurcation diagrams and the Lyapunov exponents. For example, we want to study the behavior of a very well-known discrete map, which is called the logistic map, and you can see its form over there. So in this case, we wanted to see how our map responds according to the values of each parameter R. And you can notice that for in the bifurcation diagrams, for the values of 0 until 3.5, our map has a periodic behavior. And after that value and until the end, the map goes into chaos. The same thing is presented in a different way with the use of the Lyapunov exponents on your right. If the Lyapunov exponent is negative, then the map has presented a periodic behavior. But if the exponent has a positive value, then our map is in a chaotic state. In our work, we decided to use a fixed-hand Nagumo system, which is used in neural networks, and it is actually a four-dimensional continuous system. After thorough examination, we showed that it is presenting a chaotic behavior for this set of parameters, and also it has some hidden attractors. Also, you can see the publication diagram and the number of exponent of the same system, and you can indeed verify that in this set of parameters, our system presents chaotic behavior. Here we have the phase plot of the same system according to this set of initial conditions and parameters, and it is present, and you can see that our system has a good indication of the presence of chaotic behavior. After we found the system that we will use, we decided to run it in order to produce the values that they will be used for the construction of the motion trajectories. In our case, we decided to make a small modification in the timestamp because we didn't have a stable timestamp, but we decided to be unstable, and x values will be equal to the values of the Lorentzian map. So in our case, we created trajectories that they are very hard to be predicted, and our method became more complex. After the production of these values, we insert them into two operators, as you can see over there, which are representing motions in 4 and 8 directions. We then took the integer part of these arguments, and we transformed them into motion command according to this simple rule. Also, we created a memory technique which is used the element of memory. And why is that? It's because our robot usually, in each step actually, it stores in its memory the number of visits of each adjacent cells. So in our case, if there is one cell with the least number of visits, then the robot moves in this cell instantly, as you can see in the first part of this figure. But if there are two or more cells with the same number of visits, then according to the motion command that we have created, it moves into one of these cells. We then compare the memory method and the memory-free method that we have created for both in 4 and 8 motion direction. And we show that our memory method has a superior results than the memory-free methods, because we have managed to cover almost 70% of the given area. On the other hand, the memory-free method have managed to cover only 25%. The same thing happens with motion in 8 directions. Also, we study the number of visits in each cell for memory-free and memory technique, and we show that the memory method has reduced the multiple visits in same cells, as you can see on your right. Also, the same thing happens with motion in any directions. As you can notice that we have only some areas which are in a red mark, as you can see, that and they're referring to the only 3 visits in this area. Also, we decided to have a statistical analysis of our results for motions in 4 directions. And according to the number of iterations, we showed that the coverage rate for the memory technique is far superior than the memory-free methods. The same happens with the visits, with the mean visits per visited cells. As you can notice that the memory technique has a better results in both cases. So, from this result, we can say that our robot uses a local optimization in order to select the next cell that it will move. Our memory technique improves the coverage rate and reduces multiple visits in each cell, as you saw in our figures. And as a future work, we can say that we wanted to use the same methods in different chaotic systems in order to produce more complex methods for creating the motion formats. And also, we want to implement our proposed method in real robotic systems in order to deal the challenges that they will rise. Thank you very much and stay safe and healthy.